Hi, everyone. I want to thank you all for joining us here today. My name is Dr. Eric Breckenfeld, and I'm the Director of Technology Policy here at the Semiconductor Industry Association. We're so excited to talk to you all today about semiconductor research and development, and in particular, how the 2022 CHIPS and Science Act will benefit U.S. semiconductor R&D. In the first segment of this webinar, I'll provide an overview of the CHIPS and Science Act with a focus on those sections that are particularly relevant to semiconductor R&D. I will also summarize the recently released SIA CHIPS Act R&D recommendation document entitled American Semiconductor Research, Leadership Through Innovation, which can be found on our website. Following that, we'll introduce a series of scientists and technologists from several SIA member companies to talk about their perspective on the future of semiconductor innovation and to participate in a discussion of how the CHIPS Act might best support those visions. So first up, let's discuss what the CHIPS Act actually does and what it does in particular for R&D. The 2022 CHIPS and Science Act, which was signed in the summer of 2022, allocates $39 billion in manufacturing incentives, a 25% manufacturing investment tax credit, which was scored by the CBO at $24.3 billion over the duration of the credit, and allocates $13 billion specifically in research and development and workforce investment. And although these first two pots of funding are very important for the near and medium term of semiconductor capacity and innovation in the US, it's this final bucket of money, this $13 billion that we're here to talk to you about today, and that we feel is really the most important for ensuring that long-term semiconductor leadership in the US, and to ensure that the US remains a hotspot of innovation in this area. So towards that, SIA put together a document, American Semiconductor Research Leadership Through Innovation, found on semiconductors.org, with a set of guidelines for how we believe the administration should approach this R&D funding and how, through a series of high-level goals, they might best steward this investment that's being made in R&D. We separated those into 5 key investment areas for what the National Semiconductor Technology Center and the National Advanced Packaging Manufacturing Program, 2 key provisions under the CHIPS Act R&D, what those might do to best support semiconductor research. And in brief, those 5 areas are: the NSTC and NAPMP should support the development of transition pathways for innovative technologies. That is to say, they should support a pipeline of transition from early stage research, which the United States is already best in the world at in these semiconductor areas. Make sure that there's a pipeline to transition those up into devices, and then finally into innovative products that make their way into everybody's lives. The NSTC and NAPMP should also serve to help upgrade that early research infrastructure to ensure that the earliest part of the pipeline, which again, the US is already very good at, remains a strength of the United States as we look towards 2030 and beyond, and we look at how semiconductor technologies are going to change. And that really begins at that basic research level. Materials, devices, these things are happening in universities and national laboratories. And it's very important to make sure that that infrastructure remains first class. We also think it's very important to establish and expand access for mid-stage development opportunities. So this is beyond the laboratory. This is this lab to fab transition. This infrastructure is often a lot more expensive than that early stage research infrastructure, but just as important for making sure that we are filtering out those ideas that are the most innovative, getting them up to transition, making sure that they are capable of scaling, and then finally making sure that they're able to have an impact on technologies. Beyond this pipeline of innovation, we also believe that the CHIPS Act, and in particular the R&D funding, represents a great opportunity to convene industry, academia, and government, and to set up long-lasting collaborative partnerships that can change the foundation of how research partnerships happen in the US. Many of these partnerships that can be formed using the funding under the CHIPS Act can establish sort of pathways of collaboration that can last generations. And those, by the way, can cross international boundaries as well. And towards that, and including this perspective of industry, academia, and government, we think that that provides an excellent opportunity for this final guideline, which is the promoting of a dynamic workforce so that we can not only increase the size of the domestic US semiconductor workforce, but also hone and improve the skill sets of that workforce. And by following these three areas, we believe that the NSTC and NAPMP will really be well positioned to maximize the impact of this CHIPS Act funding. So speaking of the funding, I'd like to briefly talk about what those areas that are actually receiving funding are and what areas in the CHIPS Act are authorized, but don't necessarily receive any dedicated funding yet. So as you can see from this chart, there are many activities supported under the CHIPS Act at the White House, up at the leadership level, in the Department of Commerce, within the Department of State, and in the Department of Defense as well. But only some of them receive dedicated funding as part of the CHIPS Act. And so the biggest pots of research and development funding come from $2 billion that are going to the Department of Defense for their National Network for Microelectronics Development. And then $11 billion, which is going to Commerce and NIST, which is really the center of discussion in this report. And this is to support, as I mentioned earlier, the National Semiconductor Technology Center, which is envisioned as a public-private partnership specifically targeted to pushing forward the future of core semiconductor technologies and ultimately strengthening that long-term supply chain for US semiconductor innovation. Also under that pot of money is the National Advanced Packaging Manufacturing Program. This is envisioned as a program that will stand up and support the development of advanced packaging in the US. This is an area that the US has not historically had an enormous amount of capacity onshore for, but there's an opportunity now as we move from more conventional packaging to so-called advanced packaging, where we can take some of the funding in the CHIPS Act and set up that early stage up through transition, up through final commercialization. We can build that pipeline in the US. That's what this National Advanced Packaging Manufacturing Program is for, which, by the way, we believe should work very closely with the NSTC. It's very challenging right now to separate core semiconductor technologies from packaging. The two very much proceed almost in tandem, and so they need to be closely linked. And then finally, there's an opportunity to establish several Manufacturing USA institutes, which are envisioned as more focused institutes that may push forward specific manufacturing technologies that may holistically impact the semiconductor space. Before I launch into what we talk about in the rest of the report, I think it's important to have a bit of a definition of terms and what we mean by research and development, what we mean by basic and applied research, prototyping, piloting, transition. So as we look from the perspective of a single technology, that technology will move through many stages of research and development before it finally scales to volume production and becomes products that goes into the hands of consumers. It starts at basic research, where many times we'll be exploring some innovative material or new device. When that is proven to be promising, it will be scaled up to laboratory scale devices and maybe multiple laboratory scale devices, where we start to actually make some kind of early stage workable product, maybe a research processor or something like that. As we continue to find success in this, we go up to pathfinding and prototyping, where early prototypes, maybe in almost commercial-like environments, start to get built. And we start to worry about things like yield and producing many, many devices. That's when we transition to piloting, where we look at, we have this innovative technology. Can we now look to produce many of these reproducibly with the same sets of properties in a production-like environment? And then finally, when we scale to volume production, especially in the semiconductor space, we may look to producing millions of devices or beyond to find their way into consumer hands. And what's important to understand here is that the cost of moving from each stage to the next increases enormously as we go from research up to pathfinding and prototyping, piloting, and beyond. And the US has a very well-developed ecosystem at this basic research stage, and very much so at the applied as well. But there is a bit of a gap, sometimes called the valley of death, in this prototyping and piloting stage, where we would like to transition some of these innovative technologies up into products, but getting enough funding to help usher these technologies through this valley of death has often been neglected outside of the DoD space. And I have a chart that I'd like to show that may help illustrate that to some extent and show where we believe the NSTC and NAPMP can really fall to make a difference in this research up through scaling landscape. So what we have here is a look at the funders and performers of semiconductor research and development in the United States. The half on top represents these funders within the US government. This can be the National Science Foundation, it can be NIST, it can be NASA, or the Department of Defense. And these are the agencies that provide financial support for research and development in the US. And this is plotted along where their primary areas of activity are, from basic research to applied R&D to prototyping, piloting, and finally scaling. So you can see that different groups and agencies focus on different parts of this pipeline. The bottom half here shows those institutes that perform this research. These can be universities, these can be the DOE national laboratories like Sandia, even industry labs and fabs, all have a place along this and have some area of specialization. And what I want you to notice is that although this is a very well comprehensive and well-serving pipeline, we've color-coded those that serve a broad range of activities in blue and those that specifically serve defense and intelligence purposes in green. And if you remove those, you see that there actually is a gap for those non-defense and intelligence serving funding groups and performers. And really, in our envisioning, that is where the NSTC and NAPMP can best serve this holistic pipeline, come in and help take the torch from some of these earlier stage groups and be ready to pass on the torch to private industry when they're actually ready to go to full scale up and commercialization. And so in our view, for a focus on impact, this is the best area that the NSTC and NAPMP can really specialize in to improve the pipeline holistically. And I want to end by just talking about, I said the NSTC and NAPMP will need to not only take the torch from earlier stage institutions, but also be prepared to pass it along to later stage scaling and production entities like those found in the commercial space. And what's really important to make sure that all of this comes together in a way that best stewards the public's money is to make sure that we're leveraging all of that existing infrastructure that's out there already. And so what we have here on the right is a map that shows the existing locations of production fabs, R&D fabs, and universities with significant semiconductor programs, all plotted in the US. And you can see that there are many clusters of these dots. What's very important when we look at how the NSTC can function is it will need to have partnerships with every entity across this map in some form or another, from universities and research fabs to take the torch and scale up those technologies, and with the companies as well to make sure that there is a landing pad eventually for these technologies when they need to go through final scale up. And that will be true across the full stack of semiconductor technologies. And that's what's reflected here in this graphic on the left. When I say the full stack, I mean that we will need to have innovation in materials, architectures, packaging, software, every area, for memory, for logic, for discrete and analog devices. And this will require a full effort from not only those core semiconductor companies, but also EDA vendors, equipment vendors, materials companies, those taking part in packaging, assembly, and test, and also the manufacturers of fabrication equipment. And so what we're looking at here is not only a call to action from these core semiconductor companies, but also from all companies participating in innovation and R&D in the broadest sense in the semiconductor space. And so although this webinar is the first R&D webinar, we're going to invite, what you'll be about to see, we're going to invite many of our member companies to come talk about the areas of R&D that they would like to see prioritized. We're hoping that this will be the first in a series of R&D talks where we will go on to invite speakers from companies across the full stack, EDA companies, equipment, materials, every part that needs to play a role in this ecosystem. And so with that, I would like to thank you for your attention here and introduce our first speaker. We will first go to a speaker from Intel. Please allow me to introduce Gilroy Vandentop. Gil is the Director of Corporate University Research at Intel Labs, where he manages Intel's university research investments for key internal technology and business customers. He's on the board of the Semiconductor Research Corporation, an industry-wide consortium, where he managed the SRC StarNet program and is currently chair for the governing council of the JUMP and NCORE programs. He's worked in logic technology, packaging research, extreme ultraviolet lithography, many other areas. is a deep expertise in many areas of semiconductor research. We're very pleased to introduce him to you all. Please join me in welcoming Gil Vandendop.
Thanks, Eric. Can you hear me all right? All right. Yeah, that's a nice overview. I appreciate it. I didn't bring any slides, but I have some notes. As everyone can see from Eric's presentation, is the act itself is fairly complicated, and if you look at the space and all the participants, it's that much more complicated, right? So Intel has been working with various groups, these groups in an effort to lead stakeholders to what kind of governance, what kind of structure do we need to actually embark on some of these challenges. There's the alphabet soup is long, right? I mean, all these different entities: AFF, ASA, ASIC, MITRE, SEMI, SIA, SRC, right? The list goes on. We think that Department of Commerce and NIST, probably all of us, would like to see a little bit less complicated space, right? A little broader industry consensus. We do have a little time, right? Because there's not much going on in terms of information coming from the government until February, right? When they're promising to release that white paper. So we're having discussions with all of our friends, trying to figure out, can we have a little more consolidation of our plan? And from a high level perspective, at Intel, we're hoping for a balanced and specifically industry selected board. So, there's different ways of doing governance, but, the way you pick your board is pretty important. So we'd like to see that a lot of industry input into who the board's going to be. And we'd like to see a strategy that's aligned with breakthrough challenges, right? Not necessarily aligned with pieces of infrastructure here and there, but what are the challenges that we really have to pursue to push the industry forward in the domestic sphere, right? So, and between now and February, we kind of have to wait a little bit. I'm sure the rest of you also suffer from RFI fatigue, right? We've been going through RFI after RFI, but we don't really have a structure yet. But in the meantime, like you asked, Eric, what are the key areas where Intel wants to focus, right? As part of the CHIPS Act structure. So let's call them breakthrough challenges. And the first key area for Intel is advanced litho. Right. Shrinking feature size is never going to drop down our priority list in terms of technology advancement. Right. And it's difficult. It's expensive. Access to EUV photons is not cheap. There's a limited amount of high NA tool capacity. Right. So we think that, we will have some of that capacity in Oregon. And if you're going to do advanced lithography research, it requires a community, right? You need exposure tool manufacturers there. You need photoresist manufacturers, metrology tools manufacturers. You need academic and industrial chemists, right? And of course, just your regular industrial lithographers and the semiconductor manufacturing companies as well. So it's a big community that you need to put all the pieces together to push advanced litho forward. And we think Oregon's a good place for that. Because we do have critical mass there already, right? And and we think advancing litho is going to remain to be a key challenge for the CHIPS Act and the NSTC. We won't get to sub 5 nanometer gate length transistors unless we do keep pushing advanced lithography forward. So that's one of our key interest areas. The other area is around advanced packaging, right? I'm sure most people on the call know that that's another key area for Intel. We've been pushing the state of the art for chiplet and heterogeneous integration technology. And we think this will continue to be a key vector for Moore's Law advancement, and more so as we integrate further. We have our assembly and packaging development campus in Arizona, and there's a lot of local infrastructure there, a similar type of community as the litho community in Oregon. So we want to lead as part of the NAPMP, the National Advanced Packaging Manufacturing Program. That's number 2 in terms of the priorities for Intel. The interesting thing about the packaging area is the academic community is actually relatively small compared with all of those working in semiconductors, and they're kind of in a few different pockets. So we really think we need everybody, right? All these different academic groups to work together and in a strategic effort, right? Don't try to have everybody do everything, but organize the expertise at the various institutions. And we'll need a good partnership with academia to push packaging forward. So that's the second big one, right? The other one, I think the other ones that we're all going to agree on that are a little broader are sustainable manufacturing, right? That's part of everybody's job. It'll be a priority for the NSDC and the NAPMP community. We plan on contributing there. That one's probably a little different, right? That's not necessarily a domestic priority. It's probably more of an international priority. So we'll have to figure out how to engage with other countries and other governments, I think. And we think we probably will want to start with PFAS solutions, right? That's at the top of our sustainable manufacturing list. And then I think we'll also all agree, you mentioned it, Eric, workforce development. That's a key challenge for all of us. There have been good pockets of programs across time and across the country, but the key challenge today is how do you build something that's scalable and accessible to all of the talent that we need to leverage. We need a scalable and accessible marketing program as well as a training program, right? Because it's not just the teaching, it's the attracting of these new students. Industrial engineers and scientists aren't necessarily the best marketers in the world, right? So I think, again, we'll rely on academic partnerships to help us with the workforce development challenge. Internally, we have our university shuttle program, which allows students to spin designs and then tape them out on our technology. I mean, we think that's an important part of the workforce development picture. We want to nurture the domestic hardware design talent pipeline. We also think that workforce development, maybe not everything has to fall under the NSTC and NAPMP. We kind of like what the American Semiconductor Academy has been doing, right? They've got a very inclusive and broad program proposal for workforce development. They're working closely with Semi. Semi has some experience in that area. So we've been keeping tabs and supporting those efforts as well. It's a little frustrating. You'd think that at least we could get started with workforce development stuff right away, and we wouldn't need as much structure. So actually, that's one of the things we're talking about is, maybe as partnerships in industry, could we just help them get a head start while the government decides exactly the structure and how the money gets spent. I think there's an opportunity there just to get something started early. So I don't know how much time I took, but that's about it. I'm curious to hear what my colleagues have to say about their priorities.
Gil, I'm curious.
Questions? Yeah,
I'm really curious, especially given your experience with the SRC programs. Those are very successful, long-running. SRC's been involved with DARPA, with NSF. How do you see those programs fitting into what is currently envisioned? Given what we know already, I understand we don't know a lot of concrete information about the NSTC and NAPMP, but given what we expect, how do you see those SRC programs kind of dovetailing into what we expect NSTC and the packaging to be in? How do you think it can enhance sort of the role or maybe the trajectory of the technologies that are already kind of cooking in those programs?
Yeah, those programs are quite healthy and they're quite early on in terms of technical readiness, right? They will feed into. To me, they precede this valley of death that you're talking about, right? So the CHIPS program infrastructure will help more of those ideas get into manufacturing. But in terms of how do they interact, for example, students in the SRC programs, there's, depending on the given year, there's more internships or fewer internships, right? Internships are always useful, right? Maybe longer apprenticeships in some of these programs. Probably SRC could help broaden the student population that actually has those opportunities, right? So I would hope that they would work also closely with, let's say, ASA in terms of some of these workforce development programs. So yeah, I think more internships. The sort of progression that DARPA supported the StarNet, the JUMP, and now the JUMP 2.0 program. And then they stood up ERI and ERI 2.0 to, again, help take some of these ideas and move them closer to production, right? And so that's another important piece of the picture, I think, is that type of program like ERI 2.0.
Yeah, great suggestion. Very much in line with our thinking as well. I agree that these are key feeders, and it'll be really interesting to see how technologies sort of transition up from SRC. For those of us especially who've been keeping track with at least the DARPA side of things for many years and seeing a lot of the great stuff coming out of that. Are there any?
I should mention also, SRC, the sustainability piece. I think SRC will be key there. They've started to ramp up their sustainability programs. They've got a number of PFAS abatement or replacement, research investments, right? And I think they're well positioned to step it up even further. So I think sustainability research will have to grow at SRC.
Yeah, that's a great suggestion too, and an area that is a little bit earlier in its development than some of these others that have been going on for longer. But I think an area where even a small amount of funding could make a big impact. Are there any questions or comments from any of our other panelists before we move on to our next talk?
Eric, can you hear me?
Yes.
Yeah, just to add on to what Gail pointed out in terms of workforce development, I think it's actually going to be very, very important for us to really build a diverse pipeline. I think our standard recruiting methodologies are really not going to be sufficient if you look at the real mandate of what we're trying to do with the CHIPS Act. I think really starting early through high school, 2-year, 4-year programs, and really figuring out ways to open and share facilities early so the experiential aspect of semiconductors is apparent, and really working through minority serving institutions, much more broader base with regional clusters, I think is going to be extremely important. And I think it's also very important to democratize the education towards semiconductor ecosystem, right? How do you get that out there? How do people get to see that early and understand the value? Because I think we sometimes lose that ecosystem early, right? People get caught up in the basic sciences and they don't realize the value chain of semiconductors. And I think really capturing that is going to be extremely important. And really, I'm hoping that some of these initiatives under the ASA or others that are under different umbrellas will really go after that. I think there's a real value of proposition that to be had.
Yeah, Vijay, I think that's a great point, and I absolutely agree with the need for partnerships, especially with those minority serving institutions, the HBCUs, even the tribal technical colleges. I think these are great opportunities for this. Any other comments from any of other panels or questions before we move on? All right, seems like no. Gil, thank you so much for your talk. Hopefully we'll hear more from you throughout the rest of the event today. Next, please allow me to introduce Steve Pawlowski from Micron. Steve is a corporate vice president of advanced computing solutions, where he's responsible for defining and developing innovative memory solutions for the enterprise and high-performance computing markets. Previously, Steve was a senior fellow and the chief technology officer for Intel's Data Center and Connected Systems Group. He has many years of experience leading teams in the design and development of next-generation system architectures and computing platforms. He received his master's degree in computer science and engineering from the Oregon Graduate Institute. Please join me in welcoming Steve Pawlowski.
Thank you, Eric. I did prepare some slides, or had help preparing slides, so I'm going to go ahead and share those. Excuse me. So as to begin with the premise of semiconductor research, at least through a memory vendor's eyes, we started with the realization that when I first started in the industry, data explosion really wasn't the problem, and the biggest cost of being able to do compute was actually the central computing complex and the memory and storage subsystems. First systems I worked on actually were magnetic core systems, and then they evolved to dynamic and DRAM technology as they went forward. But over the years, with the advent of AI, machine learning, IoT, big data analytics, the growth of data has been on a phenomenal pace. but the ability to actuate and actually get insight into that data, most of it still remains fairly dark in the sense of not evaluated. And we try to look at, okay, so what are some of the reasons why that would certainly happen? And first of all, one of the aspects that has evolved over the years, logic has evolved at a fairly aggressive pace, and the overall cost in terms of energy of doing compute has tended to evolve as well. But the memory and the I/O systems have tended to lag behind because most of the value was seen, was put into the logic domain, and the memory and the I/O technologies were actually seen as commodity products. And what that's done is it's created a chasm in terms of overall efficiency. It takes roughly 100 times more energy to move data from where it's stored to the CPU and the computing complex than it does to actually do the computing itself. And the difficulty of that is using wires in and of themselves. So we can try to optimize the memory as much as technology and do as much as taking advantage of the payloads associated, but you still have the fundamental delay of wires that are very difficult to get through. So recognizing that if the data is being created and it's being stored in a particular location, perhaps we should start looking at a paradigm where computing is actually moving to the data, and there's more of a tight coupling between the computing and where the data is actually stored. The other aspect is not all applications are created equally. If you look at the top 500 website that tracks the highest performing machines in the world, it has three benchmarks actually, but two fundamental benchmarks. Number one is high performance LINPACK, which tracks the actual floating point performance of the machine relative to the peak characteristics of the machine, and it is really tuned to focus more on the compute side. And then there's the high performance conjugate gradient workloads. And when you look at the overall performance compared to peak, where the HP LINPACK numbers are on the order of about 85% or higher of, close to peak performance. For the high performance conjugate gradient, 4%, typically less than 10%, roughly in the 4%, and some of them are even 1.5% of peak. And so we analyzed what the different requirements were and determined that for high performance LINPACK, the ratio of compute to memory data bandwidth is really quite high, so you can leverage the compute quite well. But on the high performance conjugate gradient workloads, which represent a growing share of the analytics workloads and AI, the byte to flop ratio is tremendous, is extremely high. So we can't come up with solutions that would leave out one particular aspect of the market, and that's some of the challenges that we've actually seen in terms of the research that we've had going forward. So as the industry has looked at this, has tried to evolve and address what would be the memory wall. How do we get more memory bandwidth and get memory closer to CPU in order to reduce the overall performance or improve the overall performance, but reduce the overall energy efficiency or improve the energy efficiency? Well, we'll come to basically there's a system power wall. And at the point where we have architectures today, it's fundamentally hard to push that paradigm farther. And so concepts have come up in terms of in-memory computing or near-memory computing, where maybe we move the data, the compute either right next to the memory, where the memory is actually mounted on top of data, and using advanced packaging technologies to be able to take advantage of that. And eventually get to the point where we have biologically inspired systems, where we do more of the analog computing as much as possible, but that only fits in certain problem sets, because analog computing tends to be slower on an individual compute basis. But if you can have large parallel subsystems, you can take advantage of the parallelism and the energy efficiency that you can get in those areas. And we believe that with significant work and looking at different materials and different architectures and different programming models, we potentially could get 3 to 4 orders of magnitude more performance efficiency than we can get out of today's systems. So the building blocks focus on, first and foremost, you got to bring the programming community along. We can't come up with some new capability and then give it to programmers and say use it. And an old colleague of mine, Steve Wallach, has always been, it's always drilled into my head over the years we worked together. The architectures that are successful are the ones that are easiest to program. So as we continue down this path of reducing and improving the overall compute efficiency, we got to keep in mind that we have a programming community and 40 to 50 years of software development that need to come along with it. But eventually, taking advantage of better logic inside in the memory devices themselves, so we can take some of that computing functionality and put it into the memory. And most of them will be determined by the application. So a deep understanding of the application and the workloads. It's not like general purpose computing, which effectively can take care of all problems. Very, instruction sets are Turing complete. You can run potentially any problem on a general purpose computer, but they tend to be inefficient. As you start moving to more domain-specific architecture design, and you get to the point where you move tighter and tighter to memory, now the programmer has to have a deeper understanding of how data is being used and implemented in those systems, and it really becomes application-specific. So what should be inspiring these new architectures and these new capabilities is not, just new materials, but also new ways of thinking about understanding the applications, understanding the use cases, and defining the architectures associated with that. And as we look at new materials beyond DRAM, and where we can go with 3D RAM and the new memory materials, they have their own nuances in terms of how we do management, which is different than we've ever had to deal with DRAM today. So those have to be incorporated in the overall design. There may be greater error rates that we have to deal with, and in endurance rates where the industry is expecting that a device can handle a number of read and write cycles for over 7 years, and the new devices may not have that capability, but you still have to provide that level of functionality for the IT ecosystem to take advantage of it. So along with the proposals of the NSTC, is underneath the NSTC governance, there are a set of coalitions of excellence. And in particular, we're discussing here the memory COE, and it's really building an ecosystem around prototyping. As a public-private partnership, and along with academia, to not only look at leading edge memory technologies and packaging capabilities, but also how we can drive supply chain resiliency. And as we define these new architectures and as we bring memory closer to computing, that we don't violate any of the security protocols. So we don't create any greater number of attack surfaces, because we're actually trying to change that boundary somewhat. The infrastructure would include clean room space and leading edge tools, kind of what Gil was talking about on the logic side. Great, imaging capabilities, design and simulation, and then integration, not only at the memory and logical interface, but also new interconnects. Focusing on, there are possible ways where areas like silicon photonics and integrating photonics in these large subsystems are starting to make more and more sense than they did 15, 20 years ago. And then, as I'd mentioned, software and being able to model, understanding how the current applications are in use and how the applications would evolve, and those which could take advantage of more of a memory logic commingling rather than the separation that they've dealt with. And then focusing on large, packaging technologies. As we look at what we can potentially get out of a DRAM subsystem in terms of performance, means we're going to be pushing, for example, TSV pad pitches down to sub-2 micron and even lower in order to be able to, realize some pretty extraordinary architectural gains. And so those kinds of capabilities, we need to basically, create this center of excellence and have a large community be able to, to be able to focus on that. And again, it aligns with the NSTC and it aligns with the national priorities, and the SRC decadal plan outlines a lot of these areas, that some of our people have actually been part of in helping define that. Most of our memory research and development in the United States, especially with Micron, is located in Boise. The idea would be that that would be the hub, but there would be a lot of satellites in various centers that could take advantage of their better places, probably more efficient places to do system modeling and capability and potentially EDA design. And we talked about workforce development, but the hub essentially would be in Boise with the satellite systems. Now, as a technical overview, we're focusing on the grand challenges, focus on a national research agenda. And the idea is that the centers of the coalitions of excellence would be entities that would be separate in and of themselves, but would actually have co-development across those. Certainly, as we look at integrating logic and memory and getting logic and memory closer, there needs to be a tight coupling between the commensurate logic coalition of excellence as well as memory. But our grand challenges, as pointed out before, is enabling high performance, efficient computing. And certainly, as I'd mentioned, reducing the design complexity, not only design complexity for how long it takes to get designs out the door, but for how long it takes somebody to figure out how to program these new systems and how these new systems can be integrated in the standard computing model, as we pointed out before. And then the ultimate goal is biologically inspired machines, semiconductors that would really, not only in the life sciences to help us solve some of those problems, but how we can be informed by biological systems on how to build potentially more efficient and more capable machines as we go in the future. The pillars for us are advanced technology, not only looking at chip stacking and vertical integration, but advanced materials and some of the new memory type materials that are out there that I mentioned before. Analog AI and neural computing actually provide an opportunity to really drive for heavy integration because those programming ecosystems are just started to evolve. And so there's an opportunity to influence and grow those ecosystems to take advantage of these new computing models. And as I mentioned, a system level hardware software co-design is actually absolutely essential. We can't build a solution, because it's the next best material, but nobody can use it because there are just aspects of it that make it non-optimal for certain capabilities. And the strategic enablers are, as they're specified today, as we've discussed before, dedicated workforce programs to grow and inspire individuals to basically become part of this ecosystem is going to be important. I'm hoping the grand challenge problems actually inspire some of those because they are unique challenges that aren't physically, impossible from a physics point of view, but just provide, there are a lot of engineering challenges that need to be solved. And then bringing up the startup and the small to medium business communities so that they can be the next generation of these companies and capabilities where we can grow the ecosystem and keep the U.S. on, at the top of the competitive landscape. I'm sorry, Eric, I only left you 2 minutes for
No problem. We really appreciate your perspective. Great talk, Steve. I actually have one quick question, and then we can see if we have any comments or questions from the rest of the panelists very briefly. But this last point you mentioned about the startup ecosystem, I'm really curious about how you see the CHIPS Act infrastructure, in particular the NSTC and the NAPMP. How can they serve, or what kinds of services could they provide that would actually add value to the startup ecosystem in your view?
Well, I think the ability to, when we talked about on the Center of Excellence, having the infrastructure and having companies being able to do prototyping, a lot of the silicon startups that I've dealt with have had to raise extreme amounts of money to do their component development. And when I first joined Micron, there was very little investment in silicon, and most of it was in storage area. And then as AI and these nice AI systems and all these chips popped up, these small companies were small silicon companies were just coming out of the woodwork, and they were trying to raise $50-100 million in order to be able to handle even their first chip. And with the complexity of these chips and the complexity of the process technologies, it's hard to get it right the first time. So I think the the coalitions of excellence in the CHIPS Act, providing access to do prototyping for those small companies could help them, at least in my opinion, get over that initial chasm of the significant cost of being able to do a silicon-based company, and those types of development capabilities.
Fantastic. Do we have any last minute comments or questions from any of our other panelists before we move on?
Just to expand on Steve's comment there and your question about the startups, the other thing that can happen, because you may have a silicon innovation that creates an impact for the system overall. And so for the startup to have to build up a prototype of the system to prove the differentiation in that silicon innovation is a huge barrier for small companies in that semiconductor space. And Steve and Gil both talked about that full stack innovation. To the extent that the NSTC creates these demonstrators or these platforms where lots of layers of the stack are there, so that someone who wants to innovate one particular dimension can do that without having to provide all the other dimensions. That infrastructure is not just the buildings. Infrastructure can actually be the system platforms. Correct. And that could be another way we can hugely accelerate innovation in our space.
Right. Awesome. That's a great point, Dave. Thanks. All right. Well, in the spirit of staying on time here, we next move to, let's see, we've changed our, here we go. Dr. Raja Swaminathan from AMD, who I believe has joined us now. Yes, indeed. Yes. Fantastic. So Raja is a corporate vice president of advanced packaging. His work is instrumental in the development of AMD's advanced packaging roadmap. He's been a leader in silicon package system architecture definition and co-design. He has extensive experience introducing innovative technologies across the silicon packaging spectrum at Intel, Apple, and now AMD. He's led the introduction of multiple novel heterogeneous architectures throughout his career, including Intel's embedded multi-die interconnect bridge, Apple's MX package architectures, high-performance fan-out, among many others. He received his PhD from Carnegie Mellon University. He's an IEEE senior member and is on the technical advisory board for the Semiconductor Research Corporation. Please join me in welcoming Dr. Raja Swaminathan.
For the introduction, Eric. You guys can hear me okay?
Yes, indeed, we can.
Okay, let me know if you can see my screen as well.
Perfect.
Okay, good. All right. So for the introduction, I just wanted to introduce the company and our key pillars overall. So as some of you may be familiar, most of you may be familiar, some of you may be not. We have leadership portfolio products with industry-leading IP in the CPU, GPU, data processing unit, FPGAs, and adaptive SoC, and significant roadmaps for continuous improvement, generation over generation, which is all powered by our key foundational pillars on advanced technology, process technology, as well as advanced packaging technologies, 3D, 2.5D, and the recently announced high-performance fan-out that we launched last week for some of our graphics products as well. And with all of this, we are delivering data center leadership, delivering innovation in the cloud, enterprise, AI, and accelerated computing. We're just going to launch Genoa today, which is our highest-end data center products. But it's all tied together with the software ecosystem, open source software, co-designed with hardware, and optimized for heterogeneous architectures with our Zen, Vitesse, ROCm, combining and leveraging software ecosystems from AMD and the Xilinx. And we've gone through a beautiful merger with all the parties sort of playing with each other. Right? So that's really our leadership technology. And our product portfolio includes data centers, as we talked about, server CPUs, GPUs, SmartNICs, adaptive SoCs with the recent Xilinx and the Pensando acquisitions. Leadership CPUs and APUs for notebook and desktop PCs, the Ryzen family, and the workstations. Top to bottom, desktop and notebook GPUs, game consoles, and now entering into the semi-custom SoC space, as well as embedded architectures, leadership FPGAs, adaptive SoCs, and embedded CPUs. The key thing that ties all of this together is, of course, the leading edge process technology that we work with our foundry partners, but all the innovative advanced packaging architectures that we are developing and will continue to develop over the next 5 to 10 years for the different spaces, lowest end to the highest end. And really, there's not a single package architecture that is going to work across the board. It's really, you're going to tune for specific power performance area and architecture. So just 2 slides to introduce our company and some of the technologies that we're working on. So narrowing it down to what we see in the National Semiconductor Technology Center, NSTC, and the packaging program. As many of you may be aware, our CEO, Dr. Lisa Su, is part of the Presidential Advisory Board, the PCAS committee, which actually pulled together a very solid set of recommendations on how the framework of NSTC and the NAPMP needs to be. And all of us on our team were very grateful to work with the team and provide that feedback. Some of the key program recommendations were have an independent legal entity where the public-private partnership and the models, it could be one, it could be a couple of those public-private partnerships really established by end of 2023 with an aligned governance of NSTC and the packaging manufacturing program. And the specific recommendation was for the Secretary of Commerce to create a board of directors to oversee both the NSTC and the NAPMP to ensure synergy and alignment of investments. Because as I think the industry realizes very well, silicon doesn't exist without packaging moving forward. It used to be a case when I joined the industry 17, 18 years back was, hey, packaging, just make sure that you don't break the silicon, was how my first program started when I was back at Intel. Now it's come the wheel has turned a full circle, and now silicon cannot scale without advanced packaging. So they have to go hand in hand, and that's why the specific aligned governance model was also proposed. Very specifically, geographic diversity for the infrastructure investments, not focusing it all on a single geo or a specific set of companies, but the prototyping capabilities should be built in geographically distributed models, encompassing up to 6 coalitions of excellence with major technical thrusts. The memory COE, which Steve eloquently talked about previous presentation, a logic COE, the mixed signal RF and power COE, and I think some of the presenters here are going to discuss in more detail about it. We believe one of the most important COEs here is this architecture, design, and tools. And the reason is, I think you can pick an example like a 3D V-cache, that example. The hybrid bonding technology was around for, I'd say, 5 to 6 years before we launched the product. But without an actual architecture to make use of it in a specific product segment with the right design tools and the EDA tools that actually can make the technology viable in a product, that's actually a very, very critical piece. Advanced packaging per se doesn't work without the advanced packaging architectures and the silicon architectures, the ecosystem tools that play into it. So I think this, I'll be very interested in how this center of excellence actually pans out and what are the feature sets that we involve in here. And then the life sciences COE, as well as the what is closest to my heart is advanced packaging COE, which is really where a lot of new initiatives need to pan out. So these grand challenges, again, we need to have almost a sort of a moonshot moment here, right? Grand challenges which really span 3 complementary areas that would benefit from large-scale nationwide collaboration, advanced computing into the zetascale era, significantly reducing design complexity as the technology nodes shrink and the advanced packaging complexity keeps increasing. It's now easier to put together the different Lego blocks on PowerPoint, but actually designing it and getting a product out requires significant design complexity, test complexity, the binning, matching, those all become pretty significant challenges that were not quite a big deal when we're doing monolithic pieces of silicon. So I think that's very significant as well. And as well as proliferating semiconductors in life sciences applications. That's also going to be a pretty key initiative. So moving on to Workforce Development Fund, our program recommendations was specifically to establish a national microelectronics education and training network by end of 2023, and upgrading the laboratory facilities and equipment, at least 50 hub universities geographically distributed across the country, including MSIs, and updating the curriculum development. Right now, I think our curriculum needs a refresher in terms of what it means to design semiconductors and what it means to design logic, what it means to design memory, how to design them together, co-design. The phrase that we use in the fabless ecosystem is DTCO, design technology co-optimization, and STCO, system technology co-optimization. So bringing those concepts into even all the way to high school or undergraduates, getting them the perspective on what it means to design complex products moving forward will be very critical. And not just universities, but also community colleges is also very critical. And hiring and recruiting at least 100 new microelectronics faculty across the nation. Support university access to industry standard resources, including EDA tools, TCAD software tools, design flows, MPW fabrication runs, as well as I think some of the previous speakers talked about having access to semiconductor foundries for teaching and research purposes. I think Gil talked about Intel's initiative, a very noble initiative in that space as well. And doing all this, the industry dynamics is also critical. So while manufacturing jobs are important, and I think a lot of emphasis has been placed on building manufacturing capability in the US and sort of fabs in the US, design is, if not equally, but more important than actually the manufacturing itself, because as we talked about earlier, a technology doesn't exist without a design. And I think that the piece of design technology co-optimization, putting them both on the same pedestal needs to be critical, and the exponential growth in the market space for labor and the industry dynamics also needs to comprehend that. I think these were the key recommendations from AMD into the PCAST as well as the NSTC and NAPMP initiatives. So I didn't have too many slides, but I'd like to open the floor for questions if there are any.
Awesome, Raja. Great to hear your perspective. Really appreciate that. And one note I wanted to make, and then perhaps a question as well, is on this topic of the design side of things. I think this is an area that, as you say, you don't have a product if you don't have a design. And I think this is something within the industry very well understood. And I wonder, in your experience in the PCAST effort, certainly ours when we interface both with the administration and of course with Congress as well, getting them to understand that through line has actually been somewhat challenging, simply because design is so much more esoteric than the manufacturing itself, even as important as it is. And so I'm curious about your experience with that in sort of helping bring that awareness about, and then also on this idea of not only the design, but also the packaging centers of excellence, these ideas, they to me, they seem very similar in some ways, in that they have their core sets of technologies that are very important, but they're also very cross-cutting in that they also cut across the other centers of excellence in very big ways. And so I'm curious to hear your perspective on that as well.
Sure. Thanks for the question, Eric. I think there are multiple questions here, so let me see if I can parse it out. I think the first question was how do you raise awareness in DC, basically, right, of what it means to do design and along with manufacturing. Actually, I'll split the answer into two parts. We have actually a very excellent government relations team within AMD, who, again, we have been coaching them on what exactly design means and what exactly fabs are sexy, right? I mean, building fabs, 6 giga fabs, or whatever number of giga fabs different companies are announcing. They sound sexy. They bring 100,000 manufacturing jobs, bring tools in and all that. Design is not, or at least when the legislators that our government relations talk to didn't quite think of design the same way, right? But again, it is a concerted effort to make them understand what the value of design is. And we used our example of, for example, the 3D V-Cache that we launched last year and some of the advanced packaging initiatives. That product would not have come to fruition, or the technology, the hybrid bonding technology would not have come to fruition without a product that is making use of it. And we actually had to go through multiple rounds of innovation. The government relations team pulled me into one of the discussions with a congressman once, and they actually are pretty interested in learning about it. So for what it's worth, I think they want to learn and they want to move the needle forward. And within Texas here, I think we've been having a very good sort of consortia that we actually initiated, the Texas Institute of Electronics. And we've had a lot of discussions with Cornyn's office and Senator Cornyn's office and Representative McCall's office on sort of walking them through what it means to co-design and develop technology and design in collaboration, right? So that's the first. I hope I answered the first part of your question. I think the second part. Sorry, do you want to add on to it, Jim?
I was going to ask you a separate question, but if you're still answering his.
I was too.
You can take a, you can take a question from Gil.
Actually, why don't we take this question? And I think I already forgot a second question, so I'm going to ask
Okay.
you to repeat it again.
One of the things I worry about is the manufacturing piece of the NAPMP, right? And you have a lot of experience in packaging, and when we start talking about packaging technology, we generally we're talking about technological advances, right? Whether they be in thermal or power delivery or signal integrity, et cetera. But those things will not necessarily bring packaging manufacturing onshore, right? So what, I mean, do you have an idea in a program like that, what we would need to do to actually bring packaging manufacturing onshore?
Good question, Gil. And this is something that we have been sort of wrapping our heads around as well. I'm sure Intel is too, in terms of what it means to bring it onshore. And I've had a lot of conversations with Tom Rucker as part of some of the panels that both of us have been on, in terms of what do we really onshore, right? I think that's a key piece that we're trying to break through. To me, I think we need to have short-term North Star goals, right? Pick 2 or 3 focus areas. We can't do all of the above that you mentioned in the short term or in the medium term. Pick 2 North Star goals. I mean, it's a idiosyncrasy when I say 2 North Stars, but pick 2 North Star goals and really focus on bringing the industry collaboration together, right? It could be, hey, bring in hybrid bonding into the United States, which is a focus area that we are trying to push with the TIE ecosystem. And it could be, we could pick a second one, and we're open for consulting on that as well. And really, and if I bring that one, it has to be an end-to-end enablement. It has to make sure that we comprehend the thermals of 3D stacking, we comprehend the power delivery of 3D stacking. It has to be an end-to-end ecosystem. And that's where a design company like us and the design team within Intel and IBM can actually help bring all of this together, right? So that's the piece. Focusing on the 2 initiatives is critical, as opposed to spreading ourselves too thin.
Thank you.
Hey, may I ask a question? Did you get your question, Gil?
Go ahead, Steve. Yep.
Hey, that was a good talk, Raj. I appreciate it. Quick question though, when we talk about design, especially in workforce development, as you well know, for every architect, it takes probably 5 to 7, people underneath to make that architecture reality. Test, verification, validation, firmware development. What do we do to inspire those types of functions in terms of the workforce development program?
So actually an excellent question, because I just scratched the surface on how to convince the legislators that design is important. Now, this is the next level of detail, right? Test verification. It took me a while to understand what verification was. In fact, I say my knowledge on verification has improved only in the last maybe 4 years or so, being in a systems company with Apple and AMD. So I'm learning as well on what are the key challenges there. Test is also going to be a very critical piece. Again, picking one initiative and driving the end-to-end ecosystem, including test, including design, including verification, would be where I think, and then focusing not just the dollars, but also the workforce investment resources will be critical, I think. Again, I don't think I quite answered your question, but this is my thoughts.
So there should be a focus on, not necessarily all tier 1 schools, but bringing in the community colleges and the
Absolutely, because let's be honest here, right? I think the different levels that you talked about, design, manufacturing, test verification, we don't need the same kind of skill sets across the board. Also, you don't need excellent science to do verification. Like you don't need a PhD in physics to do verification, right? So it just has to be across the board workforce development.
If I might just add on that, maybe Stephen, I feel that the experiential learning at an early stage is something that is really missing and very important. As I think, as Raja pointed out, not all of it needs a PhD, right? You need people at a 2-year, 4-year from minority serving institutions coming in and experiencing it. I think that has to be a clear mandate of the NSDC and NAPMP to provide that shared ecosystem. So that you can build this up. Otherwise, you're not going to be able to build the workforce that we need to meet the mandates.
And even within that NSTC or NAPMP, if there's a design focus area, you intentionally bring in interns. We do that in our company regularly, right? In my team, we bring in interns. Every summer, I have 10 interns on different areas just for them to understand what is going on. And we specifically target women and folks from the minority institutions, because I think as much as we say we use the words diversity in the workforce. I don't think we are practicing it.
Correct.
We are being intentional about it.
Okay, thank you.
Maybe
Awesome.
you can get
Great.
your second question, Eric.
Yeah, great discussion, guys. I'd love to hear more, and I have more questions myself, but I'm afraid we're going to have to move on in the interest of time.
Sure.
We're going to move on next to David Robertson, all right, here was David, and David, I think I'm presenting your slides. David is David's the Senior Technology Director for Automotive Communications and Aerospace at ADI, having been there since graduating from Dartmouth in 1985. He's worked on a variety of high-speed data converters within many semiconductor process technologies. He's worked across aerospace and defense, instrumentation, communications, and consumer devices. Beyond his role as a senior technology director, he's also an ADI technical fellow and a senior member of the IEEE, having chaired multiple committees. Please join us in welcoming David Robertson. And David, I will now share my screen and hope that I share your presentation and not mine. You can see this just fine.
Yep, there we go. Thanks. As John Cleese would say, now for something completely different. We've heard from the digital and memory gang, and I want to talk to you a little bit about semiconductor innovation in the mixed signal world. So next slide, Eric. Just because Analog Devices is not quite the household name that Intel or AMD is, quick introduction to who we are. We connect the physical and digital world together. We were founded in 1965, so 57 years old, but please do not call us mature. In fact, that's when we talk about talent. I think it's one of the things that our whole industry needs to address is we cannot let the impression go on that all the interesting stuff in semiconductors has been invented. We're actually at the threshold of some really fascinating things going on. ADI's hybrid manufacturing strategy, so half of our revenue comes from internal fabs, half of it from foundries, and our internal fabs are in Oregon, state of Washington, Massachusetts, and in Ireland. And we have design facilities globally. So we really are, like many of the speakers here, think of ourselves as a global company and looking at global markets. So next slide. So let's talk about the analog and mixed signal world. So a lot of us think of semiconductors as the brains, the processing muscle behind what's going on, and that's been hugely important. And the picture in the upper right is actually lifted from the SIA report, and you see that discrete, analog, and other quadrant down at the bottom there. And this is the weird stuff that interfaces the real world to that digital world. So we have semiconductors that need to do the sensing, measurement. There's been some good Q&A going on about metrology and instrumentation. And a lot of that starts with an analog or mixed signal semiconductor device. The connections, wired or wireless, come down to an analog problem. Interpretation and trying to augment the processing that's done in the digital domain. Security is a really, really important factor. And a lot of that is done digitally and even in the software world, but there's a whole lot of things that need to be done right at the circuit level in the analog and mixed signal world, including some things like physically unclonable functions, things like that. Finally, last but not least, power management and distribution, from data centers to handset to the implantable device in your body. There's extreme challenges and innovation required in managing and delivering power into those systems. And that tends to be an analog and mixed signal world. So for those that aren't familiar with the technology, this is that funny corner of the space that interfaces the semiconductor brains of the data center and your handset processing into the real world. Next slide. Now what is needed there differs hugely by markets and technologies. And one of the things that's a little different when we talk about the CHIPS Act, there's an emphasis on manufacturing. There's the emphasis on research and development later in the stages, which means that there's a line of sight, a connection, not only to the factory, but the commercial or strategic end use applications. So automotive, we've seen the impact, how dependent the automotive industry has become on semiconductors. And semiconductors have always been there for the last 25 years in automotive, but an electric vehicle has perhaps 4 to 5 times the semiconductor content as a conventional vehicle. Communications, silicon is far cheaper than spectrum. So people are throwing a lot of silicon at trying to get more data moved across a finite spectrum, whether wired or wireless. Consumer applications are hugely dependent on innovation in semiconductors, energy and the smart grid and what it takes to get renewables on and off the grid. Very, very semiconductor intensive things. Healthcare. So the advances that need to be made in healthcare, and not just curing sick people, but keeping people healthier. Again, huge advances required over the next 20 years in semiconductors. So this is part of how we have to attract talent into our industry. It's how we have to kind of inspire things. So when we talk about what has to happen in innovation in semiconductors, we need to keep these core markets and technologies in mind. That also helps kind of the rank and file, the average taxpayer, understand a little bit better, why should we push money into CHIPS Act? What difference does it make to me whether the data center has gotten 2x more powerful? These core markets and technologies help the sponsoring bodies understand that. So next slide. Picture on the left is extracted from the recently published SIA report, and Eric had introduced it, the five-phase model to innovation. And classically, government funding and has really focused on those first two phases, really basic research. It's also where it's very easy for competing companies to collaborate. It is literally called pre-competitive research in many cases. But that innovation needs to continue down through steps 3, 4, and 5 to move things into mass production. So these are extremely important innovations. And in many cases, design continues to be important, but we talked about verification. We talked about product engineering. We talked about test. We talked about yield enhancement. There's a whole lot of innovation that you can really only get exposed to if you can stay close to the factory. So that's one of the risks that the US puts itself at. If we offshore all the manufacturing, there's a whole lot of vital learning that we simply don't get access to. So one of the key things that we want to talk about is greater access to the kinds of problems that only surface in steps 4 and 5. And that's where the valley of death is. Eric talked about that earlier. I'll also offer up the observation that when we talk about the valley of death, half the problem is technical, but the other half of the problem is this business and ecosystem. All the elements that have to come together often requires coordination across the stack. And we talked to that a little bit earlier in this discussion. I want to bring it back up here because it's one of the things that's a big challenge and what we want the NSTC and the CHIPS Act to help address. How can we create these ecosystems that can help provide coordination across the stack? So next slide. So again, on the left, another couple of pictures grabbed from the SIA report that just remind us that remarkably, the US is today quite the leader in semiconductor research and innovation. So the industry is very healthy, it tends to be profitable, and we pour a huge amount of that revenue back into R&D. So the US spends 18% of its revenue, the US semiconductor players put 18% of that revenue back into R&D. That creates that private pool shown below of $50 billion annually as a 23 estimate. So we say, okay, so CHIPS Act puts in $5 billion. How does that really impact something when the industry itself is already putting 50 billion in there? So what we really have to think about is what can the NSTC and the other CHIPS funding do to fill in the critical gaps, to complement that $50 billion of private investment that's already massively constructive. And part of what we need to do is really convene collaborative full stack ecosystems. And this has come up from all of the speakers so far. It's about bringing players together, which is far trickier as we get closer to manufacturing, because again, this is where we start to look at each other as competitors, not just as collaborators. But it's not without precedent. Standards bodies are an example of where competitors get together to provide constructive ecosystems. I think we all saw the huge lift in the 1990s from the MOSIS effort. So a lot of this is about advancing technology and accelerating things with a little bit of coordination. But the other word that's come up frequently here is access, providing access to academics, to more factories and things that are going on, providing access to the small and medium-sized company. The other thing that we all share, where we all, the same tide raises all the boats, is talent. And we've talked about education and workforce development, but talent. What we see is that a lot of the players in our industry are going to end up working for 2 or 3 or 4 companies across over the course of their career. Gil, I have not ever worked for Intel. I think I'm the first speaker here today that hasn't worked for Intel. But again, we all share this talent pool. So I think this is something that's also really, really important. And when we look back on this 10 years from now and judge whether the CHIPS Act really made a difference, my prediction, it'll be the impact on the way talent got developed and the way we attract talent into our industry that will be the most important. And with that, open up for questions or even hand it to the last speaker so he has a chance. So Raj has a chance to jump in too.
David, thank you so much. Very eloquently put, and you've stolen many of my figures, but that's okay because I actually plan on stealing some of your slides as well for the future. So I think we'll have a little bit of back and forth there.
Excellent. The royalties, we'll work out the cross royalty payments.
That's right. We'll solve that on the back end. I think maybe we have time for, well, I actually suspect we don't have time. What I will instead do is thank you for getting us back on time. And we will now go to our final speaker who's going to bring us home here. So finally, we go to Dr. Vijay Narayanan from IBM. Vijay is an IBM fellow and a strategist for the physics of AI and a senior manager for PCM and AI materials at IBM. He leads an international team in the development of analog accelerators for AI applications and novel materials for advanced CMOS logic. He pioneered high-K gate dielectric research, and such devices have come to form the basis of all recent IBM systems processors and most low-power chips for mobile devices. He received his PhD from Carnegie Mellon University. He's an IEEE senior member and was elected a fellow of the American Physical Society. Please join me in welcoming Vijay.
Thank you. Can you hear me, Eric?
Yes, we can.
Okay, thank you. So let me start here and try to make up some time. Okay, so thanks, Eric. So I thought since I'll be the last, it's really to look at a high level and what the key priorities and opportunities might be. And it's a perspective from an IBM lens. We are a full stack company that does everything from materials to cloud infrastructure. So for us, innovation across each part of the stack is going to be critical. So as I look at the key innovations that key priorities that we think are very, very important and has been touched on by many of the previous panelists. One is to really democratize access to advanced semiconductor technologies. This is going to be critical for the startup and the university ecosystem. And this will allow us to really spur design innovation, which is going to be very important and to help bridge the lab to fab. Second is to really accelerate an open chiplet ecosystem. This is going to be critical as we look at our next generation of system architectures, many of the domain-specific architectures that was talked about by a few of the earlier panelists. And finally, to reduce the cost of chip design by EDA modernization. This is going to be extremely important. It'll also democratize the access and the ability to deal with compute and accessing it when needed. So if I start off with the AI imperative, and I bring this up as an example of what's going on with compute, as many of you are aware, the model sizes and parameters are now going to billions of parameters, going up exponentially, and to be able to keep up with that, the computation need is also going up dramatically, and in many cases, it's going up 2x every 3 months. These are very significant challenges, and we have to be able to address this completely. And our thought process is to be able to do this you will need innovations across the stack. It's just not going to be good enough to just have a materials innovation or an algorithmic innovation. You've got to do it across the stack from materials all the way through accelerators and software. And to touch upon something that was brought up before, we really believe that one of the key pieces is to continue to improve compute efficiency, approximate computing or reduce precision math while maintaining accuracy is something that goes along with CMOS scaling and is a critical way for energy efficiency. But over and beyond that, something that has been touched upon by Steve before is really on one Neumann bottleneck. So really to focus on near memory compute to get it as close to compute as possible, the memory, to mitigate the data bottleneck. Then, of course, ultimately to completely eliminate and do the compute in the memory itself. Of course, none of this is fully possible without having an end-to-end where you're actually increasing the memory bandwidth with advanced packaging or heterogeneous integration. And there's an image of that on top where you have the compute and the bandwidth only, but when you combine the two together, it makes up for either of them. It's greater than the sum of its parts. So advanced packaging and heterogeneous integration are going to be extremely critical. And I know the previous speakers talked about it a lot. I think it actually drives the industry. It enables the deficiencies of scaling that one is coming across. When we look at what are the foundational elements of some of the advanced technologies that are there, some of the semiconductor innovations have come from many of us on the panel here. But nanosheet is an example where we've gone from a FinFET to a gate-all-around technology structure, and this is going to be the basis for all of the future logic technology and continued innovations, looking at stacking them vertically, or even more disruptive to look at a vertical transport transistor that we've talked about at IDM late last year. These are all critical innovations, but one needs to be able to really access them in a democratized manner, and that's going to be very, very critical. In addition, looking at things in the back end scaling beyond copper, novel materials, process integration, how do we actually enhance and accelerate that is going to be extremely critical and important. And just to, support what Gil had talked about, high-NA EUV is, you can't talk about next generation technology without EUV and lithography innovation. This is going to be extremely critical and important basis. So these will form the foundational basis for many of the technology innovations. And so keeping that in mind, wanted to really provide this democratized access to advanced semiconductor technology. A couple of examples are shared here where you have a nanosheet-based technology with a PDK that is accessible in the form of an MPW, and where you can now innovate on delivering IP and functional circuit blocks. In addition, to be able to do aspects like in-memory, near-memory compute, you could embed NVM in a leading-edge CMOS, and this will again be enabled with an MPW run with an enhanced PDK and relevant IO IP. And finally, to bring it all together, next generation HI technologies that Raja talked about and actually going to be critical is these three chiplet ecosystems for high bandwidth applications, along with these RDL for multi-level high density chiplet interconnects. These are examples of technologies that need to be developed, and because they accelerate the rate of adoption, and they have to be provided. And the hope is that the STC and APMP will enable this kind of basis of technology that people can come in, utilize, and innovate on, and therefore build the lab to fab and really be able to demonstrate the hard tech that currently is challenging. Finally, on the open chiplet ecosystem, this is really to accelerate the system design level innovation. And we've talked about an open chiplet system as opposed to a proprietary one, because it helps us break down the barriers for innovation. It's also very important to build up these standards to be able to deal with affordable chiplet prototypes and really have workload-based chiplet platforms. And this will allow small and medium-sized businesses to actually work alongside large companies
And along with these standards, one can see that this could be a very critical piece that is currently missing, but it will allow access across the board to startups, companies, and academia. Now, as was pointed out before, the industry has done standards in the past, brought them together to really innovate. And there are many emerging standards today, bunch of wires, OMI, UCIe, and Compute Express that are all coming up for communication protocols. And I think these are very solid and strong evidence of utilizing standards to really build up the ecosystem that's needed. Finally, the EDA modernization is a very extremely important part. It will allow for designers to scale their workloads. I think one of the key aspects here is to be able to transition these design flows to the cloud, and basically to be able to access compute when needed, and to be able to do a lot of this in parallel. But of course, this is an opportunity to create algorithms to leverage these kind of microservices in the cloud for these kind of increased parallelism. Also important is to really provision usable cloud resources, another bottleneck typically. So really this kind of EDA modernization is going to be extremely important. Utilizing AI and ML driven improvements to really now figure out how to take those design flows and really enable a scalable workload execution, and also using AI and ML to improve design capabilities. And you can see that in some ways on the right figure where one has to be able to improve the physical design, but also be able to execute things like OPC with security across the entire plane, and also be able to parallelize the compute so that you get it when you need it. All of these can really improve the overall turnaround time and quality of results. Using the service and hybrid cloud infrastructure, one can really see significant improvement and enable for this platform designers to continue to scale their workload. So with that, I will stop. Let's get 3 minutes back.
Hey, Vijay, before we go on to questions, you may want, we're getting a little bit of crosstalk. It seems to be going back and forth between your computer microphone and maybe your Bud microphone or something. You may want to just make sure that it's set to the right microphone in your settings. We could hear you, but it was cutting out a little bit here and there and making it a little bit hard to understand at parts. But anyways, but thank you so much for that. I think we have a few moments now to turn to our panel and see if there are any final thoughts or questions anyone would like to share.
Yeah, I'd like to sort of echo what Vijay said, right? The EDA ecosystem is going to be extremely critical. What we are realizing as we scale those 3D technologies, the tools don't exist today, and we're essentially building or making homegrown tools, and all the 3D EDA vendors needing to come together and pushed by some of the design houses is going to be one of the key pillars of DTCO as well.
So Vijay, I mean, what level of abstraction do you think is possible for hardware design? I mean, do you think it will eventually be possible to democratize that a lot more, similarly to software design?
I think so. I think some of the bottlenecks that exist is really doing things in a sequential manner as opposed to really being able to do parallelized things, really being able to use the compute when you need it and use a whole lot of it by utilizing a cloud enablement. I think that's going to be critical because that tends to be a bottleneck in many of the things that that the design houses tend to do. So I think that's the first step, the EDA modernization, and I do feel that it's going to be critical for what we want to do within the NSTC and NAPMP, because it's going to be reducing that cost is a big barrier to be able to do some of the larger workloads.
But tough trade-off because I see it as a tough trade-off because a lot of times the way you achieve abstraction and simplification is you accept a given level of, you compromise a little bit on efficiency. And so many of the systems now are power constrained, and we really need to simultaneously produce huge breakthroughs in power efficiency while still making the system level design approachable. And so that's a very constrained very challenging problem, which I think should capture the interest of smart folks. I mean, I think it's a really tough nut to crack, and it's definitely something that we want to be the leaders on domestically here.
So it's one of the key grand challenges for the NSTC, you would say?
I think so.
Yeah. Yeah, I think so.
Awesome. Thank you very much, everyone. We've hit the 30-minute mark here at the end of the webinar. So I want to thank all of our speakers for joining us here today. I want to thank everyone in the audience for sticking with us to the end of the 90 minutes. I hope you all found this educational and inspirational. And our goal at SIA is to have this be the first of many research and development talks as we continue to track what's going on with the CHIPS Act and in particular the R&D parts of the CHIPS Act, what we can expect, and hopefully what kinds of innovations we're going to look to from our companies, from academia, and from government as this all moves along. So thank you all so much, and we'll see you on the next one.
Thank you. Bye.
Thank you. Thanks. Bye.